Welcome to another one of our introductory videos related to temperature metrology. And in this session we're introducing the water triple point cell. The water triple point is critical to temperature metrology. Up until May 2019, the Kelvin, the unit of thermodynamic temperature, was defined by the water triple point. Since then the definition's changed on the SI and it now relates to the Boltzmann's constant. But the water triple point remains essential to disseminate the ITS 90 and is used every day in calibration laboratories to check standard platinum resistance thermometers and other types of temperature standard. So what is the water triple point? Well, let's start with an ice bath, commonly used to check thermometers at temperatures close to 0 degrees C. And with an ice flask, we have water in two phases, water as a solid, ice, and water as a liquid in equilibrium at atmospheric pressure. And if we prepare an ice bath very carefully and with best practice, we might be able to get an accuracy of about 0.01 degrees C. But the water triple point is the unique temperature at which water can exist in all three phases simultaneously: water as a solid, ice, as a vapour, and as a liquid. So this is a water triple point cell. At the moment it's at room temperature. There's no air in here, it's been vacuumed. Now if I was now to create some ice inside the cell, then we'd have all three phases of water in equilibrium. We'd have water as a solid, ice, as a vapour, and as a liquid. And that gives us the unique temperature of 0.01 degrees C or 10 millikelvins. So with a well-prepared ice bath, we might be able to have a temperature with an accuracy of about 0.01 degrees C. With a water triple point cell, will easily be 10 times better than that. And water triple point cells come in different sizes. This is a small water triple point cell and can be used in a portable temperature calibrator. These cells here would be used more with laboratory standard thermometers and might be used in a dedicated apparatus or a liquid bath. Now, the temperature inside the cell will be the same when these cells are realised. They'll all be at 0.01 degrees C. But with the small cell and a relatively small thermometer, it can work quite well. But if we've got a large thermometer, like a laboratory SPRT, such a large thermometer, if we put this into a tiny cell, the thermometer would never reach thermal equilibrium with the cell, so we'd have a high uncertainty, not because the temperature of the cell isn't correct, but because the large thermometer won't reach thermal equilibrium with the small cell. So when the water triple point cells are manufactured, all the air is vacuumed out, leaving a vacuum, and we can check that's still in place. This isn't a handle, it's called a McCloud Gauge, and it's just a simple means for us to check the integrity of the cell. I can invert the cell, fill the gauge with water, and I just want to check that there's just the smallest of bubbles left when I do that process. So that's how we use the McCloud Gauge. With the B series of cells, it doesn't have the McCloud Gauge in quite the same way, but we can do the same by inverting the cell and filling this tube with water to check that there's no air bubble. And also, if we gently shake the cell, that very distinctive metal clack sound again gives us confidence that there's no air inside to cushion the sound of the water against the glass. So with an ice bath, we said the temperature will be close to 0 degrees C, perhaps with an accuracy of 0.01. But with the water triple point cell, at least 10 times better. But with a small cell like this, if we needed a calibration certificate for it, and we may well do for traceability, Really, an uncertainty of 0.5 millikelvin would be appropriate for a small cell. These larger cells, these can be calibrated with a calibration uncertainty on the certificate of less than 0.1 millikelvins. So at the moment all these cells are sat at room temperature. So how would we create the water triple point cell? How would we use it to calibrate a thermometer? Well, one way would be to put dry ice inside the thermometer well or the reentrant tube, and we could slowly build ice onto the reentrant well, and that's a method commonly used. Or we might use a cold metal rod and introduce that into the cell. But at Dicetech we have an ice mantle maker, which is a heat pipe, a long thin heat pipe. We can cool the top and we can use that to create the ice. We have a separate video showing how to prepare the cell and how to create the water triple point using that method, and the link is shown. Another way is to supercool the whole of the cell. So because the water is so pure, we can chill a cell like this to perhaps close to -6 degrees C and it'll still be liquid. But once we've supercooled the cell, we can shake it to initiate a freeze. So we could use a portable calibrator, a dry block, or a larger liquid bath, depending on the type of cell, to supercool the cell and then make the water triple point that way. And again, we have a separate video showing how to do that, and the link is shown. So once we've created a water triple point cell, we've got our ice mantle and we're ready to use it, we need to maintain the cell. One low-cost way of doing that would be, after you've created the cell, perhaps with dry ice, to put it into an ice flask, surround it in a duo flask of crushed ice, and the cell will stay there for some time. But it can be more convenient to use perhaps a portable dry block calibrator for the smaller cells, or a larger dry block, or even a liquid bath set to close to 0 degrees C to maintain a created water triple point cell. And for laboratories with a few cells which are being used very frequently, there are dedicated apparatus available, such as the water triple point maintenance bath, which can maintain up to 4 cells at the water triple point for up to 4 weeks. So finally, some practical thoughts. Water triple point cells are affordable. This one costs less than a specially drilled metal insert for a portable dry block calibrator. The larger ones, made in quartz glass with a calibration certificate, need a larger investment, but they're still quite affordable way for a laboratory to get millikelvin uncertainty and check in the standards. So they're very useful devices to have. The glass, if I drop it, it will break, so I just need to be careful how I handle and store it, but they're not so terribly fragile. But even so, it's a good idea to have 2. That way, if one does get broken, there's still one remaining for use. We've got a lot more information on the website, the link shown below. We've got very technical guides on how to make the cells. We've got information on why a laboratory should use a water cell and a gallium cell. We've got research papers. I would encourage you to look at those. And finally, thank you very much for watching the video, and be sure to like and subscribe to be kept up to date.